more important in statistics than confidence interval. Let me elaborate a little bit on that. Are you familiar with the Higgs boson?
Nope.
It's a particle in theoretical physics that was predicted 50 years ago by a mathematician.
Mm-hmm.
He said this particle should exist. Actually picked up a nickname called the God particle, because this is the particle or field that gives everything mass. In other words, when iron goes through the universe, what gives it mass? Why is it heavier than hydrogen? Well, turns out that it's this Higgs boson. Okay? Now, the existence of this particle was predicted 50 years ago based on mathematics only, not physics. And then they built this $7 billion Hadron Collider over in Europe. And it's big enough that it can discover these newer particles that might exist. In other words, humans had never had a particle accelerator that could produce the kind of energies needed to find the Higgs boson until 2 years ago. And they discovered the Higgs boson. Now, the discovery process in science is based all about statistics. You never discover anything with 100% certainty. What you do is you discover a new particle and you say, I am certain that that is not a particle we've ever seen before with 99.99994 certainty. That's the best they can do. And in fact, that's called 5 sigma because it's 5 standard deviations. Okay? You're familiar with the most important probability distribution there is in statistics, and that is a normal distribution. Well, sigma is the measure of spread. In other words, I can have a normal distribution that looks like this, or I can have a normal distribution that looks like this. The difference between those two is sigma. Sigma is a lot bigger up here than it is down here. Sigma is standard deviation, and it's a measure of the spread of that normal distribution. Okay? Now, if you know, well, here's what they know, is that if I go out, that right there is the mean, x bar. If I go to this point, and that is x bar minus 1 standard deviation, and if I go over to this point, and that is x bar plus 1 standard deviation, then I know that the area under that total curve, 65 or what is it, 66% of it is between x minus sigma and x plus sigma. So I kind of have like a 66% confidence interval. If I was from the mean minus 1 sigma to the mean plus 1 sigma. Most of the problems they're going to give you in statistics, you're going to have the mean and you're going to have sigma. Okay? So you can figure these things out. Now, if I go out 2 sigmas, in other words, if I go, let me use a different color. If I go out to here, well, now I know that 94% 95% of the curve, the area under the curve, the total curve, is in that blue area. It's x bar plus or minus 2 sigma. That's 95% of the area. If I go out 3 sigma, that area represents 99, I think it's 99.4% of the area under the curve, and that's 3 sigma. Okay?
You were talking about 5 sigma before,
In order for physicists to proclaim a discovery, they have to have certainty out to 5 sigma. Now, what does that translate to? We can see that 4 sigma is going to be a really high number. Well, 5 sigma is this, 99.99994. That is the confidence level that they have that they found the Higgs boson.
So it's just very confident then.
Yeah, very confident. Now, along the way, the first thing they discovered was 3 sigma. In other words, before they announced the discovery of it, they were 99.4% certain of it.
Mm-hmm.
And then they did more tests, they got more data, and they got to 4 sigma, and the moment they hit 5 sigma, that's what scientists need, is 5 sigma to announce something as a certainty. And you can see that it's still not quite a certainty. Okay? So, let's get back to confidence level. I think that shows you that new discoveries are always about confidence levels. They're never 100%. They're 99.99% or something like that. But you just don't know something for certain is true. All right. Let's talk about a college. It has 5,000 students. And they decide that they are going to market their college to high school students by advertising the average IQ score of their students. With me?
Mm-hmm.
So you got 5,000 students. Well, they didn't give you enough money to measure the IQ score of all 5,000 students. But they gave you enough money to measure maybe 500 students or 50 students 10 different times. Okay?
Mm-hmm.
This is the way statistics works. When you have a universe that is too big to actually find out what the average IQ is, then you take a sample, an SRS. Standard random sample. Okay? And we're going to start out with 50 students. And those 50 students produce an average mean, an X bar, of 112. Okay?
Mm-hmm.
And what I know about these kind of SRSs is that they produce a normal curve. In other words, that's going to be 112, and there'll be some standard deviation amongst those 50 students. Okay? With me?
Yeah.
If I were to next take another random sample of 50 students, what am I going to get for an X bar?
If you
Going to get 112 for sure?
No, but when
No,
if you
I might get 114.
Mm-hmm. It should be close though, right?
It should be.
Unless you're
We'll call that
like,
one 1. we'll call this one 2, and then maybe we'll do a third one. And that might give you 109. Okay? Now, here's the theory. And this is an important concept. If the original 50 students fit a normal distribution, and I were to take 10 of these samples and plot the average mean of each sample, I am still going to have a normal distribution. Okay? I just did 3. Well, what's the average of those 3? It looks to be about 112, right?
Mm-hmm.
So that's going to be my mean of my 3 different tests, and may not be exactly the same shape as the normal distribution of 50 students. Maybe this shape will be more like this. Okay.
Mm-hmm.
Now let's take 10 samples of 50 each. Better yet, let me show you a picture that I have downloaded from my statistics book. You can see what they've done over here, starting with figure 10.1. Okay, that's a standard random sample. Sample size is 50 students. They got an X bar of 112. They did another one. They got an X bar of 109. Wow, that must have been in my subconscious. I was not looking at this page when I made up those numbers. That is scary.
They're all 52.
That is really scary. I got the exact 3 numbers. And it was only in my subconscious. But anyway, now, so they did some number of these samples. It says ... meaning we don't really know how many they did. But they did some number of them, and they got a figure 10.2. Okay? In other words, our goal here is to figure out what the actual average IQ is of a student at this university. I don't have enough money to test all 5,000 students, but I got enough money to do a few samples of 50 students at a time. And what it's going to tell me is what the average IQ is with a confidence level. Hold on a second. You got to be kidding me. I don't have the one page I wanted on here. Hold on one second. This is important. Otherwise, I wouldn't take your time with it. Move this picture to my computer so that we can both see it. Hold on a second. God, I hate this. I'll tell you what, there's few things that frustrate me more than trying to type on a smartphone.
Yeah.
Well, I'm constantly hitting. I got skinny fingers, and I'm constantly not hitting the correct letter. All right, hold on. I should get to my computer any second here. And when it does, I'll bring it up. All right. So what we have here,
Oh, I've seen one of these.
yeah. In other words, what this means, these, this was 150 sample. That was the mean, that was the low, and that was the high. Okay? This is another one. There's 25 of them here. Notice, out of the 25, this one right here, that has a mean and a left end and a right end that is not in the 95% area. In other words, the 95% area goes out to 2 standard deviations. So if I'm outside of that area, there's a possibility that I might do a 50 number sample, 50 students, and end up with this one down here. The other 24 are all within my confidence interval. This one is outside of my confidence interval. Well, my confidence interval is 95%. That's 2 standard deviations. In this particular problem, they give us the standard deviation. So I can figure out what my confidence interval is. It's the X bar of the 25 different samples plus or minus 2 sigma, because that gives you 95% of the area under that curve.
When you do the 2 sig plus 2 sigma?
It's plus or minus. It's plus 2 sigma to the right, it's minus 2 sigma to the left. That gives me 95% of the area under that curve. Now, what does that mean? Go ahead, ask me a question.
What do you do for adding the 2 sigma again?
Well, notice this point is X bar.
Yeah.
This point is X bar plus 2 sigma. This point is X bar minus 2 sigma.
So that's just kind of stating the range it's in?
Well, and what that means on any normal distribution curve that's symmetrical is that 95% of the area under the curve lies within X plus or minus 2 sigma. So that if you were to do a 26th sampling, in other words, we've got 25 here. If I were to do a 26th one, I would be 95% confident that it would fall in that area right there. I would be 99.4% confident that it would fall X bar plus or minus 3 sigma. I would only be 66% confident that it would fall in the area X bar plus 1 sigma or S bar minus 1 sigma. So it all depends on sigma, and that tells you what the area under that curve is, and that is the same as your confidence level. Now there's 2 words. There's confidence interval, which is this, and there's confidence level, which is this. Means you have a 95% certainty that if I were to do a new sampling, it would fall within X bar plus or minus 2 sigma.
So the confidence interval is the X bar plus or minus, and then the
Yes.
sigma, and then the level is just the percentage?
Confidence level. And like I said, there's nothing that's 100% certain. Let's pretend for a moment. I think I can make this a little bit more understandable. Let's say that X plus 2 sigma, I don't even know what sigma is on this. I don't care. I'm going to assume sigma let's see, if this is 112 IQ, and we'll assume a sigma takes it out to 142. Okay? And on the other side is 82. So, if this is 2 sigma away from the mean, then it tells me that 95% of the people that I come into contact with on a SRS are going to have IQs between 82 and 142.
Okay.
Okay? So, let's take it back to the Higgs boson. Let's say you came across somebody that had an IQ of 350. And somebody tells you, is there an alien amongst the human race? And if there is, they're going to have a dramatically higher IQ than everybody else. So let's say you come across a person that you don't know whether it's a person or an alien, and he has this 350 IQ. Is that an alien or a human?
Probably an alien.
With what confidence interval? You're right. I would say that's an alien also. But it's
what you said earlier, isn't it 95?
Well, it's based on how many sigmas 350 is away from 112.
112 plus 2 sigma?
Well, 1 sigma is 15 points. Sigma in this case is 15 points. So this is like 240 divided by 15.
So it's a little bit, it's just a little bit out.
This is like 10 sigma. Okay? Physicists would have declared this guy an alien a long time ago. The moment his IQ maybe reached 225. Because they would have only been looking for 5 sigma. Now, I'm not sure that's exactly a correct metaphor for the Higgs boson, but it's close. This is how statistics is used to determine stuff. You know, does cigarette smoking cause cancer? Yes, with 5 sigma accuracy, it does. Yes. Okay. There's all kinds of questions you might posit. Are they true or false? Is drinking wine better for you than drinking beer? This can be answered. Yes. If you did, well, you can only answer that. You can't really answer it scientifically. You can only answer it statistically. You can test a bunch of people who drink wine, and you can test a bunch of people who drink beer, and whichever one has heart attacks earlier, you can come up, but you can never say yes or no. You can only say yes with a certain confidence interval. That's the only thing you can ever say. There's no way I can say this 350 IQ person or alien is an alien. I can't do it for certain. It's possible maybe Einstein would have measured out at a 350 IQ. I don't know. Maybe Einstein was from the future. Maybe he was an alien. Who knows? But that's the way they do this. Is the further away you are from the mean, if you know it's a normal distribution, then the less likely it is. In other words, they have what they call outliers. Okay? Even a normal distribution usually has outliers. You might have somebody that has a 10 IQ. And we do actually have humans that have 10 IQs. And we know that there are people that maybe have 200 IQs. I've never really read of anybody that's had a measurable IQ greater than 200. But there's still a possibility of it. Okay? We don't know. We just haven't encountered it yet. So if we found a human that had a 350 IQ, we wouldn't be able to make a positive statement about it. We'd just be able to say we have a certain confidence interval. You can say that 99.4% of humans on the planet Earth are going to have an average IQ of 100. That's the way IQ works. 100 is average. In other words, X bar is going to equal 100 plus or
Wait, are you
minus.
talking about for that? Isn't it 112?
No, that was for that college. I'm talking about
Oh, okay.
all the humans
Sorry.
on the planet. The way the IQ scale is designed, 100 is average. Okay?
All right.
But let's say in my example here, sigma was 15. So if I go out 3 sigma, which is 45, now I would be able to say that everybody that I would run into would be most likely to fall in that range. 99.4% of them would. Because I've gone out, oh no, I went out 3 sigma. Yeah, that's X bar plus or minus 3 sigma. And that includes 99.4% of the area under that normal distribution curve. So if I'm testing a random person, 99.4% of them are going to have IQs between 55 and 145. If I find somebody with a 200 IQ, he's way outside that. He's not in the 99.4 percentile. He's in the 99.9 percentile or higher. And that's what confidence interval or level means.
Mm-hmm.
Pretty much nothing is certain. It's only certain to a certain degree. They still don't know for sure if they've discovered the Higgs boson. Because all they have is a 99.999994% likely.
Which is pretty much.
Well, it's a number. Yeah, it's pretty much. But notice they did not announce its discovery when it was 99.99%. That was only 4 sigma. Science, and this is somewhat arbitrary. I don't think there's any math behind this, but physics have decided, or science has decided, that 5 sigma is what you look for. Once you find something within 5 sigma, you can declare it fact. And that's what they did.
Why did the sigma end in 0.4?
I'm sorry, what?
Why did they go to 0.4 instead of like 0.9 with the sigma?
Like I said, I think that's arbitrary, meaning that somebody pulled it out of their ass or out of the sky or something.
All right.
No, seriously. There's no mathematics. This is 5 sigma. 99.99949 and then a 4.
Because it just seems kind of unusual that there's just
it's kind of random, right? It's just, like I said, it's
like they just randomized they rolled the dice the last number.
That's the definition of arbitrary. We don't know whether we should go 0.999999998 or should we go just 0.994. We don't know. Just somebody has decided that this is a good standard to use, 5 sigma. And I think I have given you the limit of my knowledge on this subject.
Mm-hmm.
Okay?
Clear some stuff up.
So hopefully I've helped you a little bit.
Mm-hmm.
But please believe me, I really do want to help you more. But for me to do that, you got to send me problems. And you got to send them to me in long enough in advance that I got a chance to work on it. You can't send them to me an hour in advance because I might have the hour ahead of you filled up tutoring, so I don't have any time to look at them. So you can send them a day in advance. Then I guarantee I'll look at them. If nothing else, I'll go to the book and I'll find similar example problems. That's the way to do these things. If you get a problem that you don't know how to do, go to the chapter and find a sample one, an example one, rather. And that usually tells you how to do the problem. That's the method I use. If I'm not expert at something, I go looking for their examples.
Mm-hmm.
All right. This session actually took longer than I thought it would, but probably because I just talked and talked and talked. I don't think I have anything to add to that.
Thanks. That helped clear some stuff up.
All right, Sam. Good luck to you, and I'll talk to you next time.
Thank you.
Bye-bye.